Statistic process to hyperbolic geometry. Introduction. Hyperbolic geometry is a mathematical model of spacetime that depends on actual inner forces. In the background, these forces are stochastic and probably deal with thermodynamic properties. We'll travel from the Pythagorean geometrical concept of means, at the door of statistics, to the interpretation of the Bernoulli random walk. The coincidence is remarkable. This is a basic model for the fundamental physical effect of Zitterbewegung that manages 1D motion. Besides, there is indeed a relationship between hyperbolic plane geometry and the Euclidean plane geometry. This geometrical diptych will help to connect the Bernoulli random walk and the Pythagorean circle to the hyperbolic Minkowski plane. Surprisingly, the Euclidean to hyperbolic relationship will introduce a link between time and standard deviation of velocity. The theory of Alain Connes will provide an interpretation. The Pythagorean half-circle of means, the keystone. It comes from the Pythagorean school. The various forms of average for two numbers adopt the geometry of the circle. When the two numbers a and b are represented by their length on a common segment, their arithmetic mean is the radius of the circle, whose diameter is the segment. The geometric mean is the length of the vertical segment from the half-circle to the caesura between the two numbers. Harmonic and quadratic means find also a simple interpretation. That's a very fundamental property that opens a link between statistics and geometry. This anecdotal fact alone is not, however, a pure geometrical case, with metrics for instance. We'll see later that the Pythagorean half-circle can map a genuine hyperbolic geometry. For what reason? Geometry, which is based on physical observations, should depend on the fundamental forces that shape our space. And the essence of these forces is probably stochastic. We'll introduce the Zitterbewegung of Dirac and Schrödinger that probably deal with the Higgs field. Bernoulli random walk, the expression of fundamental forces. Let's imagine a binomial stochastic process that determines a 1D motion. After each time period tau, one tosses a coin to jump right or left at the velocity c. If the coin is not fair and alpha is the probability to go right, after n trials. The average number of right steps is n alpha and the variance is n alpha, 1 minus alpha. Let's transpose the binomial process to motion. The average drift. The motion or drift dn after n trials is n right steps minus the remaining number of left steps. So, the average drift dn is 2 alpha minus 1 times the length of n steps. The variance sigma dn square of the random walk is also proportional to n alpha, 1 minus alpha, as in the binomial process. By eliminating the parameter alpha, the relationship between the standard deviation sigma dn and mean dn is generally an ellipse whose height is proportional to the square root of n. In the special case where n equals 1, the standard deviation and mean of the random walk are simply linked by the circle of radius c tau. The binomial random walk measured at the scale of 1 trial is a Bernoulli's random walk. What about velocity? The average velocity. The velocity Vn after n trials is dn over n tau, so equal to 2 alpha minus 1, c, and the variance sigma Vn square is now inversely proportional to n. The relationship between Vn and sigma Vn is also an ellipse, but inside the limit circle of radius c. For the Bernoulli random walk, v1 and sigma v1 define a circle of radius c. What about the link between the Bernoulli random walk and the Pythagorean half circle? Bernoulli process and Pythagorean half circle. For the drift, the two numbers are 2 alpha c tau and 2 1 minus alpha c tau. The arithmetic mean is c tau, the atom of motion. Thus, the standard deviation of the drift sigma d1 is the geometric mean of 2 alpha c tau and 2 1 minus alpha c tau, so the square root of 4 alpha 1 minus alpha square c tau. For velocity, the two numbers are 2 alpha c and 2 alpha 1 minus alpha c. The arithmetic mean is c, the atom of velocity. The standard deviation of the velocity sigma v1 is also the geometric mean, so the square root of 4 alpha 1 minus alpha square c. The Pythagorean half circle of means fits the statistical case of the Bernoulli random walk, with the chances 2 alpha c tau or 2 alpha c to jump on the right side. Short summary. We just showed that the Bernoulli random walk fits the Pythagorean circles of means. Let's go now to the hyperbolic world. The Bernoulli random walk and the Minkowski's hyperbolic geometry. Map from circle to hyperbola. We can build a map from a point E on a circle to a point H on a hyperbola. See my YouTube post hyperbolic but still Euclidean underneath. In a nutshell, E and H are on the line of rational parametrization of the circle, that comes from C, and the abscissa of H is obtained by inversion of that of E, according to the circle. If the coordinates of H are the time for the horizontal axis and space for the vertical one, it is a point in a Minkowski hyperbolic plane. As a consequence, the ordinate of E is velocity. Let's assume first, we'll explain why. H can be represented by the hyperbolic angle phi called rapidity, then its coordinates are cosh phi, sinh phi. Velocity is implicitly in the Minkowski plane, sinh phi over cosh phi, so equal to tanh phi. The point E is located by the Euclidean angle theta. Then its coordinates are cosine theta, sine theta. The angle theta is named the Gudermanian of phi. The concept of Gudermanian provides relations between phi and theta. Sine theta is equal to tanh phi and inversion is explicit, as cosine theta is the inverse of cosh phi. Thus, velocity is explicitly the ordinate of E, being sin theta equal to tan phi. Complex and split complex layers. The Minkowski plane has a hyperbolic metric and depends on split complex numbers, x plus jy with j2 equals plus 1. The plane for the point E has a Euclidean metric and depends on complex numbers, x plus iy with I2 equals minus 1. The passage from E to H is relative to either transaction matrices T1 and T2, or equivalently split quaternions Q1 and Q2, to manage their different complex natures. Digression, Poincaré and Klein-Beltrami disks. Incidentally, one can recognize as the place of the Poincaré disk, orthogonal to the horizontal axis, that will represent E and H by a common point P, with the hyperbolic metric. P is the stereographic projection of H from C. this hyperbolic space, the straight line between the point P and another point Q becomes an arc of circle. The external circle displays explicitly the limit to infinity, that is normalized here to unity. There is also a place of the Klein-Beltrami disk, orthogonal to the horizontal axis, that will represent E and H by another common point B, with another hyperbolic metric. The point B is determined by the stereographic projection of H from O. But it's also the orthogonal projection of E, on an axis parallel to the velocity 1. The straight line between B and another point C is still a straight line, but the position of the middle of the segment reflects the hyperbolic metric. The hyperbolic distance between B and C is half of the logarithm of P minus B over BP plus times CP plus over P minus C. The position of B from O is then provided by the hyperbolic measure that involves V, half of the logarithm of 1 plus V, over 1 minus V. That's the rapidity phi, corresponding to V. We have actually, phi equals arctangent of V. The same hyperbolic metric in the Klein-Beltrami's disk depends on alpha, half of logarithm of alpha over 1 alpha. Back to math, latent at the bottom of the Pythagorean half circle of means, there is a Klein-Beltrami disk with its hyperbolic metric, half of logarithm of A over B. One last remark, the Klein-Beltrami disk is usually defined as the orthographic projection of some surrounding hemisphere. The half circle is to some extent a cross-section of this hemisphere. Back to the circle, relationship with the Bernoulli random walk. The consideration of velocity with the circle and its associated hyperbola is well established. But what about the abscissa of E? We may be tempted to superimpose on the unit circle the half circle of velocity for the Bernoulli random walk. Then the abscissa of E can be the standard deviation sigma V of B. But is there a physical effect that allows such notion next to the notion of time? The Zitterbewegung. Schrödinger named it Zitterbewegung, the equivalent in German of jittering motion. The promising track is in the Dirac's equation. The point H, that can be a free electron, undergoes a kind of random walk at only plus C or minus C, the Ceilreity of light. That's the solution of the Dirac's equation where plus C and minus C are the eigenvalues of the associated operator. Velocity is an average. Surprisingly, the development of this simple 1D concept helps to revisit all the aspects of the kinematics of relativity, when maintained to one space dimension. This is meaningful in the Minkowski plane. The Zitterbewegung is the very instantaneous motion of a massive particle, that doesn't have mass just when switching from plus C to minus C. The frequency f of the Zitterbewegung is very high, far from the resolution of any instrument. F equals 2 times the energy E of the particle over h, or 2 times m square c over h, when at rest. So tau equals h over 2e. This atom of time tau helps to feed the description of the Zitter by a Bernoulli random walk. The instantaneous phenomenon is at the scale of n equals 1. Let's recall the series of embedded ellipses. The Zitter is not perceived in the bandwidth of our observation instruments, where the time frame of the necessary interaction implies that n is far greater than 1. In a classical observation, the standard deviation of velocity is very low, sigma Vn is less lower than c. The Zitterbewegung can probably be modeled, to some extent, by a Bernoulli random walk, at least for the mean velocity and standard deviation. In the theory of Dirac, mass is emergent and is the result of the back and forth motion. For Roger Penrose and others, this back and forth motion is due to the interaction with the Higgs bosons. In this hypothesis, we have an example for the forces we were looking for, that shape the geometry of the quantum relativistic spacetime. It's time to sum up. 1. The Bernoulli random walk fits the Pythagorean circles of means. 2. The Zitterbewegung can be modeled by the Bernoulli random walk. 3. The map from the circle to the Minkowski hyperbola fits the Bernoulli random walk, for velocity and standard deviation that can be indeed physical by the Zitterbewegung, but should time behave as the inverse of the standard deviation of velocity? Modulo some imaginary process. The fusion of concepts on the Minkowski plane. Let's assume that the abscissa of E is the standard deviation sigma v of the velocity v, its ordinate being obviously an average velocity v. For the moment, the quantities we compute here are adimensional. That authorizes the passage to inverse. In the Bernoulli random walk, we've talked of time and space in terms of numbers of seconds and meters. In a Minkowski diagram, time and space are distances in unit, c times second or cs. The inversion sigma v to time requires a common set of units, adimensional spacetime in cs units and adimensional velocities in c units. Thus, to respect the common geometry, for a null velocity, sigma v equals 1/t equals 1. The Gudermannian relation between the Euclidean plane and the hyperbolic plane pushes forward into a subtle equivalence, time in c second unit and the inverse of a velocity deviation in c unit. Modulo some imaginary number as the Euclidean plane is complex and the hyperbolic one, split complex. This is equivalent to state that usual time t in second relates to the inverse of an acceleration av, in c per second unit. Is there now some known evidence that relates time to a standard deviation, or equivalently time to an acceleration? The thesis of Alain Connes. Time, variability, imaginary thermal time. There is indeed a long-lasting quest for the origin of time. The profound thesis of Alain Connes is that the fundamental variability of the world is stronger than the notion of time, that only emerges from. The clues we have, in one hand is a standard deviation that can represent variability and in the other one, time. Isn't it a particular illustration of the Connes principle? See YouTube post.
Alain Connes, Temps et aléas du quantique.
He proved in his thesis that non-commutativity that is linked to uncertainty provides an evolution mechanism. Readily. If the statistics of Boltzmann is associated to a Hamiltonian H, the weight function phi operating on the observable A will be phi of A equals trace of A exponential of minus beta h over trace exponential of minus beta h. The 1t parameter automorphism. Alpha t of A equals exponential of the imaginary unit ht times A times exponential of minus the imaginary unit ht. It obeys to the KMS condition, so phi of AB equals phi of B times alpha of A with the new index I beta. Not only this automorphism gives an evolution mechanism, but it offers a way to restore anyway a kind of commutativity within the weight function. The automorphism gauges the magnitude of the non-commutativity by an attempt of compensation. Last but not the least, the compensation mechanism involves a surprising concept of time. I beta equals IH bar over KT, imaginary and related to temperature. We'll get benefit of this latter dimensional property to come back to the first notions of deviation, variability, uncertainty. But, the Minkowski plane is not explicitly connected to thermodynamics. Piece of luck, there is a dimensional tool that helps to connect I beta to kinematics, the Unruh-Davies effect. Dimensional conversion from thermal time to dynamical acceleration. According to the sophisticated Unruh-Davies theory, the acceleration A of an object can result in a black body radiation at a temperature T. This is still perspective and can be at least applied to the radiation of black holes, theory of Hawking. But no matter, we've got the dimensional presumption that time can be equivalent with the thermal beta and the inverse of an acceleration. The final step, in the quest of melting the Bernoulli random walk and Zitterbewegung, with the map from the circle to the Minkowski hyperbola, is to choose the unit c tau instead of cs, and the acceleration A, to be sigma v over tau. What can be sigma v over tau in the Zitterbewegung? An acceleration of a different kind, supposed to prevent the massive particle to remain at the celerity of light. Why not? It should rather be isotropic deceleration in fact. In that perspective, massless particles receive a null acceleration. Deceleration is max for v equals 0. It's equal to 2mc3 over h. Simple math like this can drive us into hyperbolic digressions, true or false, hard to say, but that gives the illusion to connect however to the ancient myths and philosophies, the precise point where Alain Connes leads us today by a concrete scaffold that reaches the Egyptian nimbus. Jet and Nia on the flow of Nile.